In Chapter 2, we talked about straight line motion or linear motion, and in Chapter 3, we're going to talk about two-dimensional motion, or motion that takes place in a plane. The most common two types we're going to study is projectile motion, which is something like kicking a football or throwing a baseball. We're also going to study uniform circular motion, things that move in a circle. When we talk about two-dimensional motion, all of our vector quantities are going to have both an x and a y component. So when we talk about something's position, you can think of it like a coordinate plane where it has both an x and a y. Same thing with velocity, it'll have an x and y component. Acceleration can have an x and y component. The position vector that we're going to use we're going to call R. Now, if you wanted to know what the magnitude of R is, it would be the magnitude of its x and y components combined. In fact, you could write it like the magnitude of R, sometimes we use absolute values for magnitude, would simply be the square root of its x component plus its y component. Now, if I draw a picture, here's our y-axis, here's our x-axis, and let's consider we might have something that's moving on a path that looks something like this. At some time, it might be at this point, I'll call that point 1. I can draw a position vector, and I think I'll use blue to draw this position vector that represents it, and it would start at the origin and go to that point. So right there, that vector I'm going to call R1. You can look and notice that R1 goes a certain amount on the x and a certain amount on the y. So the x and y coordinates would be the same thing as the x component and the y component. Now, at some later time, it might be right here. Call that point 2. If I drew that position vector, it too would begin at the origin, but it would go all the way back to here. That would be R2. Now, if I want to talk about an average velocity, I know that the average velocity is the displacement divided by the time interval. And you remember, displacement is your change in position. I'm going to draw the displacement in a different color. Instead of drawing the displacement in blue, let me go ahead and draw that for us in purple. The displacement vector is your change in position. You were here, and now you're here. So your displacement vector would look like that. That's your change in position. That tells us how far the object moved from one point to the other. Now, this velocity will also have an x and y component. It would simply be that if I wanted to talk about the average velocity in the x direction, it would be the change in x. In other words, that x component, how far did it go? Notice the change in x was here, now it's here, it's about that far over a time interval. Or I can talk about the average velocity in the y direction. How far did I move in the y direction? What's my y displacement for a particular time interval? Average velocity means just what it did when we were doing linear motion, but when we did linear, we had this or we had this. When we're doing two-dimensional, we actually have both. You'll notice one thing that you might not have thought about. The average velocity is a vector quantity. It's going to point in the same direction as the displacement, and that makes sense. If you're traveling northeast, that's your displacement. You would expect an average velocity to be to the northeast. Now, if I want to get an instantaneous velocity, all I have to do is make that time interval very, very, very short. Instantaneous velocity we won't put the line over it, but we will put our little arrow. Our little arrow just reminds us this is a vector quantity. It would be equal to the limit as my time interval approaches 0. As I make that time interval very, very small of the displacement over the time interval. So it looks just like it looked when we talked about linear motion. If I draw a picture, slightly different picture, but similar. There's my X, here's my Y. If I have something, and let's say it travels in a path, again, we'll make that path look something like this. Notice that the instantaneous velocity, at this point, it's going in this direction. At this point, it's going in this direction. Right at the top, it's going horizontally. The velocity vectors are always going to be tangent to the path of the object. The instantaneous velocity is always tangent to the path. Now, let's move on and let's think about acceleration in a plane. This brings us to section 3.2 in your text. Acceleration in a plane. Average acceleration, we defined before, is just a change in velocity divided by a time interval. If we look at this, we know average acceleration is a vector. It has to point in the same direction as the average velocity, also a vector. So the average acceleration has the same direction as delta V. Notice that's not necessarily the same direction as the velocity. Probably isn't the same direction of the velocity. It's in the direction of the change in velocity, and that's really important. If we look at a vector situation, let's draw, here's some object, and it's being thrown, and we know that there's the x-axis, there's the y-axis. If we look at the velocity, we draw this velocity with a different color. We'll use purple, we'll draw this velocity. Right here, the velocity is tangent, it must be pointing generally that direction. Call that V1. And right here, somewhat smaller velocity maybe, here's V2. Notice the velocities change. The direction of the velocity is changed. It also changed the size of the velocity vector. So anytime either the size of the velocity changes or the direction of the velocity, we know we have an acceleration. The change in velocity is going to be V2 minus V1. So anytime you do a change, it's final minus beginning. Or if you prefer, since they're vectors, we're going to add v2 plus opposite of v1. Let's draw those vectors. We'll start with v2. So v2 is pointing pretty horizontal. Maybe we draw that. I really kind of wanted it to point more horizontal. Let's go. There's v2. So v2 is pointing horizontally. v1 is pointing up and over. So v1, negative v1, would actually be pointing fairly much down. To get that change or that total, I start at the beginning, I draw to the end. That's the change in velocity, or that's the direction of the acceleration. It's not intuitive, but our acceleration appears to be pointing pretty much straight down. And that is correct. In fact, I tried to model this what would look something like what goes on when you kick a football. When you kick a football, the acceleration is straight down because the acceleration is due to gravity. Okay? Notice, so the direction of the acceleration is the same as the direction of the change in velocity. One thing you'll notice is that the acceleration always points to the concave side of the path. Okay. Always points towards the concave side. So if you think of this being like this acceleration always has to point in towards that side. If we want to talk about instantaneous acceleration, the acceleration at any particular moment in time, all we do is make that time interval really small and we get a limit. So the instantaneous acceleration, which we usually just represent with an A, is the limit as the time interval approaches 0 of the change in velocity over change in time. It's possible that some of you are taking calculus right now, and if that's true, you're going to learn that limit is actually a derivative. So if this was a calculus-based course, we could say that the acceleration is the derivative of the velocity function, dv dt. And these are actually still would be vector quantities. We're not doing that in this course, so don't worry. But basically what this means is they've taken, this has made this what we call infinitesimally small. That dt is called an infinitesimal. Do want you to remember that if you have an acceleration, it represents any change in velocity. You can speed up, that's an acceleration. You can slow down, that's an acceleration. Or you can simply change your direction. If you're driving a car, you actually have 3 things you use to control the car that all cause acceleration. One is the gas pedal. We think of that as being what causes the acceleration. One is the brake pedal, and the other one's the steering wheel. Now, when velocity and acceleration are parallel, basically that means they either point in the same direction or they point in opposite directions. But if the velocity and acceleration are parallel, the object moves in a straight line. if they're in the same direction, if the acceleration points this way and the velocity points this way, well, remember, acceleration will point in the same direction as the change in velocity. That means any change in velocity will also be this way. What's the result? Well, if the acceleration and the velocity point in the same direction, speed increases. The object's going to go faster. If they happen to point in opposite directions, what we see is if we have, say, an acceleration that points to the left, but the velocity vector points to the right, then our change in velocity, however big it might be, is going to also be to the left. The result of having a change in the opposite direction is that speed will decrease. So, velocity and acceleration point in the same direction for linear motion, that means you go faster. Velocity and acceleration point in opposite directions for linear motion, it means you slow down. Now, what else can happen? When the velocity and acceleration are perpendicular, means that they're at right angles. What you see is that the speed is constant. But the direction changes. If you have something that has a velocity in this direction, but the acceleration is pointing in this direction, that means the change in velocity will be down. A few seconds later, what you'll see is the velocity will be pointing at a different direction, more like this. Because that acceleration effectively is pulling that velocity down. It's accelerating downward. Just like if you threw a baseball horizontally and it was initially moving this way, the acceleration due to gravity would cause that baseball to fall. So what we see is, while they're perpendicular, you have a constant speed, but the direction will change. Now, if they're not parallel and they're not perpendicular, which could happen a lot of times, then both the speed and direction of the velocity can change. If we think about kicking a football, when you kick a football, the path of the football looks something like this. What you see is, at this point, the velocity looks like this. And at this point, it looks more like this. And at the top, it looks pretty much horizontal. And at the here, it looks like this. Notice it's going to get faster as it falls, just like it was fastest right here where they kicked it. What's going on? Well, in this case, the velocity and acceleration they're not parallel, they're not at right angles. Right here, the acceleration pulls down. In fact, the acceleration we know is negative 9.8. Same thing here. This acceleration is pulling it down. It's going to change its direction. Notice here, since they're almost in opposites, it causes the velocity to decrease. It not only changes the direction, but it decreases the speed. But on the way down, this same acceleration is going to cause that speed to get faster. So it's slowing down or losing speed on the way up. it's gaining speed on the way down, because on the way down, these two point more or less more in the same direction. Okay. Let's look at just an easy example. Suppose we have a remote control car on an empty lot. At t equals 2 seconds, we're going to call that T1, that's 2 seconds. The car has a position of 4.0 meters, 2.0 meters. In other words, this is a vector quantity, but they've given us the x and y components of that vector. Somebody's marked out a grid on this parking lot. So we have our car at the point x equal 4, y equal 2. At the second time, which happened to be at 2.50 seconds, the car is in a new position. Now it's at 7.0 meters, 6.0 meters. Okay, so we want to find a couple of, first let's find the x and y components of the average velocity. All right, the x component of the average velocity, or Vx, is simply the change in x over the change in time. Well, I look here and see how my x position, it's gone from 7 to 4, so final minus beginning, change in time, final minus beginning. And we find that in the x direction, we get an average velocity of 6 meters per second. If we look in the y direction, we want the change in y over the time. Y was gone from 2 to 6, so we have 6 minus 2. That time interval is that same 0.5 seconds. So we end up with 4 meters over half a second. It's 8 meters per second. So it's actually traveling faster in the y direction than it is in the x direction. That makes sense. It moved 3 meters horizontally, but it moved 4 meters vertically. The second part of this question says, find the magnitude and direction of the average velocity. In other words, can you put these x and y components together? Well, I hope so, because that's what we learned to do back in chapter 1. If I want to put these together, the magnitude of the velocity is going to be the square root of the x component squared plus the y component squared. Now remember, we just use the Pythagorean theorem when we're trying to add perpendicular vectors, or if we're going to add vector components. You probably should already know the answer to this one. The x component was 6 squared. The y component was 8.0 squared. We solved this, and the magnitude of the vector comes out to be 10.0 meters per second. To get angles, remember we use tangent inverse. Theta is equal to the tangent inverse y over x. So 8.0 over 6.0. This is quadrant 1. They're both positive. So it came out to be 53 degrees. So if we measure this from the positive x-axis, then our velocity is 10 meters per second at 53 degrees. Now, let's talk about the same car. Suppose that we know the velocity as well as the positions. Not an average velocity, but the actual velocity. Suppose that they tell us at time t1, the x component of the velocity was 1 meter per second, and the y component of the velocity was 3 meters per second. At time 2.5, that's t2, the x component of the velocity was 4 meters per second, and the y component of the velocity was 3 meters per second. Let's see if we can find the components of the acceleration, or the average acceleration, and then find the average acceleration. So, average acceleration in the x direction, change in Vx over time. Well, final minus beginning, 4 minus 1, time interval 2.5 minus 2. And we see that the average acceleration in the x direction will come out to be 6 meters per second squared, because it's meters per second divided by seconds. However, look at y. The change in the y component of the velocity, Vy, is 0. It was going 3 meters per second vertically at 2 seconds. It was going that same 3.0 at 2.5. So our change in velocity here is 0. So our acceleration is 0. If I put those two together, adding a 0 magnitude vector is not going to change this. If I do the Pythagorean theorem, I'm going to get the square root of 6 squared plus 0 squared. So my acceleration is simply 6.0 meters per second squared. I even know what direction. It's accelerating in the x direction. There's no y component. I don't have to do that tangent theta. I could, but all I really need to understand is that this is going at the positive x direction, which is 0 degrees. Or you could have written in the positive x direction. Okay, the next part of this chapter is about projectile motion, and projectile motion is a pretty lengthy conversation. I think I'm going to save those pages to make this separate video. And jump all the way to section 3.4. And section 3.4 is about uniform circular motion. So we're going to deal with uniform circular motion before we talk about projectile motion. Uniform circular motion comes up a lot. It's going to be really important when we talk about things like satellites, things that move, orbit in circles. Jumped over to section 3.4, uniform circular motion. When I say uniform, what I'm really meaning is constant speed. So this is constant speed in a circle. That could be a satellite in orbit, that could be a car driving around a circular track, that could be taking a toy and tying it to the end of the string and swinging it around so that the toy moves in a circle. We can think of lots of examples. All right, so let's consider something that's moving in a circle. Let's think about it. If it's when it's right there, and I'm going to let the circle say it's traveling clockwise. When it's right there, the velocity vector points towards the right. Remember, the velocity vector is always tangent to the path. If I come down here at some other point, say right here, actually tangent to the path there would point straight down. If we come over here someplace at an angle, tangent to the path points something like this. But the velocity vector is always tangent to the path. Now, it's clear the object is accelerating, and we know it's accelerating because the direction is changing continuously. However, we also know it's traveling at a constant speed. It isn't speeding up, and it isn't slowing down. So that means if the only thing is changing, that the acceleration must be perpendicular to the path, or perpendicular to the velocity vector. If only the direction is changing and the speed is constant, those are perpendicular. So our acceleration would point something like this. This would be a right angle, this would be a right angle, this would be a right angle. In fact, what we see is that since the speed is constant, the velocity is perpendicular to the acceleration. That little upside down T is just a math symbol. It means perpendicular. If they weren't perpendicular, if some part of it wasn't perfectly at a right angle, it would either be speeding up or slowing down. So what we see then is that V is tangent to the circle. A tangent line, remember, will only touch at one point, and that the acceleration points toward the center. When we have an acceleration that points towards the center, we call that a centripetal acceleration or radial acceleration. Centripetal comes from, I believe it is the Greek root, could be a Latin root, but it is a root that means center seeking. Radial, of course, comes from the word radius. So it points along the radius of the circle, or it points towards the center of the circle. I think I'll leave my picture. Like I say, centripetal means center seeking. Don't mix it up with the word centrifugal. You've probably heard the word centrifugal. That would mean center fleeing. This is center seeking. The acceleration actually points towards the center. This is also called radial acceleration. So we have centripetal or radial acceleration. I'm not going to derive the formula. It's a little bit tricky with the vectors, so we're going to just give that to you. The radial acceleration is equal to v squared over r. You may also see this written with the little c for centripetal. This book uses a capital R when we have a definite radius of a circle. It's a little confusing. We usually use a lowercase r in geometry, but that's okay. In this case, v is equal to the speed, and r is equal to the radius of the circle. Really can't be equal to the velocity for a couple of reasons, but one is that velocity itself is continuously changing, but we need that uniform speed, that speed that does not change. Let's get an example. It says that a 2005 Corvette claims a lateral acceleration of 0.92 g. That's 8.9 meters per second squared. If this is the maximum centripetal acceleration that can be achieved without skidding, remember that means it's a maximum acceleration that it can have traveling in a circle without sliding off the road. We don't want to skid. The question says, if the car is traveling 45 meters per second, so we have a velocity or a speed of 45 meters per second. That's about 101 miles per hour. What's the smallest possible radius? Find the minimum radius without skidding. So, our acceleration, our radial acceleration, is v squared over r. We know that as r gets bigger, look at the formula, the amount of acceleration will go down. It takes less acceleration, which means, and we're going to learn in the future, it's going to take less force if we have a big circle. It takes more acceleration or a larger force to move in a tighter circle. So we want to find that smallest possible value. If we put that our radial acceleration is 8.9 meters per second squared, our speed is 45 meters per second squared, and we want to find r. Now, occasionally people get a little bit mixed up on how to solve for things when they're on the bottom. If you have trouble with that, make it look like a proportion like you did it in middle school. If you put this over 1, it becomes real easy to see that r will equal this 45 meters per second squared over 8.9 meters per second squared. 45 squared Oops, turn it on. This gives us 2,025 meters squared per second squared. Remember, when you square a quantity, you have to square the units as well. Divided by 8.9 meters per second squared. Notice all of the units will go away except for meters. That's real important because it should come out with the right answer, right units if we're doing it right. So divided by 8.9, we get about 227. Well, to two significant comes out to be 227 and some change, but we only have two significant digits. So about 230 meters. So if the radius can't get any smaller than that, if that radius was smaller, our acceleration would be too great and we would go skidding. We could not handle it. This car only has a maximum lateral acceleration of about 8.9. Let's do one more. There's lots of carnival rides that we can talk about where we have people moving in big circles. There's one where people stand up next to the edge and it spins around and the floor drops out and you still feel like you're pressed to the back, that you're being held. So let's look at or just even on a merry-go-round, hanging onto the outer edge of a merry-go-round. So we've got passengers in a carnival ride that travel in a circle that has a radius of 5 meters. So whether this is a merry-go-round, it doesn't really matter. We've got some type of ride. They make one complete orbit in time in 4 seconds. One complete orbit in 4 seconds. The time for a complete orbit is normally called the period because it's a repeating motion, and that's a capital T. So our period is 4.0 seconds. Draw a picture. Can't hurt. So we have a radius that's 5.0 meters. We have a speed. We don't know. We have the period. We know that it takes 4 seconds to go all the way around. Well, when something moves in a circle, the speed can be found by the relationship that is going to be the circumference divided by the period. So in this case, it's going to be 2 pi r over t So I end up with a speed that's about 7.85 meters per second. I kept an extra space because I know I'm going to round to 2 at the end. So my centripetal acceleration, v squared over r, is 7.85 meters per second squared. That's the speed squared, divided by the radius. Notice that when we get done, one of these meters, because that's going to be meters squared, second squared, is going to divide off. So we'll get the right units, and that's 7.85, not 7. So 7.85 squared divided by 5 meters. And I get about 12 meters per second squared. Occasionally, they'll ask you to express an acceleration in terms of the number of g's. It's really easy to do. If I want to know how many g's that is, that's 12 meters per second squared. I know 1 g is 9.80 meters per second squared. I just treat a g as a unit of measurement. 1 g is equal to 9.80. So if I do 12 divided by 9.80, comes out to be about 1.2 g's. Now I think I did a little rounding at some point, but so in terms of g, or the acceleration due to gravity, it's 1.2. I'm going to stop here. I'm going to make a second video for this chapter that deals with projectile motion.